In this lesson, we're going to explore one of the most important discoveries in quantum statistical mechanics, how Enrico Fermi and Paul Dirac solved the mystery of electron heat capacity in metals. In the early 1900s, physicists faced a serious problem. Classical physics predicted that electrons in metals should contribute significantly to heat capacity, but measurements showed something completely different. First, let's understand what heat capacity means. Heat capacity is the amount of energy needed to raise the temperature of a substance by 1 degree. Mathematically, heat capacity C equals the change in heat dQ divided by the change in temperature dt. According to classical physics, specifically the equipartition theorem, each particle should contribute 1/2 kBt of energy per degree of freedom. The average energy equals 1/2 times Boltzmann's constant kB times temperature T per degree of freedom. Electrons moving freely in three-dimensional space have 3 degrees of freedom, one for each spatial direction. This means the classical prediction for electron heat capacity should be 3/2 nkB, where n is the number of electrons. But when scientists measured the actual heat capacity of metals at different temperatures, they found something shocking. Here's a graph showing temperature on the horizontal axis and heat capacity on the vertical axis. The red line shows the classical prediction, which says heat capacity should be constant at all temperatures. But the measured data, shown in green, tells a very different story. At low temperatures, the heat capacity is much smaller than predicted. It increases gradually as temperature rises. Notice the systematic deficit at low temperatures. The measured values are far below the classical prediction. This was a major puzzle that classical physics could not explain. So why does this happen? What is wrong with the classical theory? This question puzzled physicists for years. The answer came from quantum mechanics, specifically from Wolfgang Pauli's exclusion principle discovered in 1925. The Pauli exclusion principle states that no two fermions, particles like electrons, can occupy the same quantum state simultaneously. Electrons are fermions with spin 1/2. This means they must obey the exclusion principle. Imagine energy levels as shelves. Each shelf can hold at most 2 electrons, one with spin up and one with spin down. At absolute zero, electrons fill the lowest available levels first. At absolute zero temperature, electrons fill all the energy levels up to a maximum energy called the Fermi energy. All levels below are full, all levels above are empty. The Fermi energy EF equals h bar squared over 2 meters times the quantity 3 pi squared n to the 2/3 power, where n is the electron density. In 1926, Enrico Fermi and Paul Dirac independently developed a new statistical distribution that incorporated the exclusion principle. They derived what we now call the Fermi-Dirac distribution function, which gives the probability that a quantum state at energy E is occupied. The Fermi-Dirac distribution, f of E, equals 1 divided by E to the power of E minus mu over kBt plus 1, where mu is the chemical potential. At zero temperature, this becomes a step function. States below the Fermi energy have f equals 1, meaning they're occupied. States above have f equals 0, meaning they're empty. Here's the Fermi-Dirac distribution at very low temperature. Notice the sharp drop at the Fermi energy. Almost all states below EF are filled. Almost all above are empty. So why does this solve the heat capacity problem? The key insight is that only electrons near the Fermi energy can be thermally excited. At finite temperature, only electrons within about kBt of the Fermi energy can absorb thermal energy and move to higher states. Electrons deep below the Fermi level cannot participate because all nearby states are already occupied. The fraction of electrons that can participate in thermal processes is approximately kBt divided by EF. This is a very small number at room temperature. Let's calculate the actual electronic heat capacity using Fermi-Dirac statistics. The electronic heat capacity, CE, is proportional to temperature T. We write CE equals gamma T, where gamma is the electronic specific heat coefficient. The coefficient gamma equals pi squared over 3 times nkb squared divided by EF. Notice how it depends inversely on the Fermi energy. Let's compare this to the classical prediction. Classical theory predicted C equals 3/2 NkB. Quantum theory predicts gamma T, linear in temperature. The ratio of quantum to classical heat capacity is approximately kBT over EF. At room temperature, this ratio is typically around 0.01 or 1%. Let's work through a concrete example using copper metal at room temperature. Copper has an electron density of approximately 8.5 times 10 to the 28th electrons per cubic meter. The Fermi energy for copper is about 7.0 electron volts, or 1.1 times 10 to the negative 18 joules. At room temperature, 300 Kelvin, the thermal energy kBT is about 26 millielectron volts. So kBT equals approximately 0.026 electron volts at 300 Kelvin. The ratio kBT over EF equals 0.026 divided by 7, which gives approximately 0.0037 or less than 1%. This means only about 0.37% of the electrons can participate in thermal processes at room temperature. The vast majority are locked in filled states below the Fermi level. One of the most important predictions of Fermi-Dirac statistics is that electronic heat capacity should be linear in temperature at low temperatures. Here's a plot of electronic heat capacity versus temperature at low temperatures. Notice the beautiful linear relationship. This is a direct consequence of Fermi-Dirac statistics. How do we verify this experimentally? The challenge is that the lattice vibrations, called phonons, also contribute to heat capacity. The total heat capacity has two contributions. C total equals gamma T plus AT cubed. The linear term is from electrons, the T cubed term is from phonons. The phonon contribution follows what's called the Debye T³ law at low temperatures. This was derived by Peter Debye using quantum mechanics for lattice vibrations. To separate the contributions, we plot C total divided by T versus T squared. This gives gamma plus A T squared. When we plot C over T versus T squared, we get a straight line. The y-intercept gives us gamma, the electronic specific heat coefficient. The slope gives us A, the phonon coefficient. Let's summarize the key differences between classical and quantum predictions in a comparison. Here's a comparison table. Classical theory predicts constant heat capacity of 3/2 NkB. Quantum theory predicts gamma T, linear in temperature. Classical theory assumes all electrons are active. Quantum theory shows only a tiny fraction near EF are active. At low temperatures, classical theory fails completely, while Fermi-Dirac statistics matches experimental data perfectly. The development of Fermi-Dirac statistics was a pivotal moment in the history of physics. In 1926, Enrico Fermi in Italy and Paul Dirac in England independently derived the distribution function. Neither knew of the other's work initially. This work immediately resolved the electron heat capacity puzzle that had plagued classical physics for decades. It showed that quantum mechanics was absolutely necessary for understanding condensed matter. The insights from Fermi-Dirac statistics led to our modern understanding of metals, semiconductors, and even the structure of stars. It's one of the cornerstones of modern physics. Why was this discovery so revolutionary? Because it showed that quantum mechanics fundamentally changes statistical behavior, not just the behavior of individual particles. Let's look more closely at how temperature affects the Fermi-Dirac distribution. Here are Fermi-Dirac distributions at 3 different temperatures. The blue curve is close to 0 Kelvin, showing a sharp step. The green curve is at medium temperature, showing some smoothing. The red curve is at high temperature, showing significant spreading around EF. The width of the thermal broadening region is approximately 4 kBT. Only electrons in this energy range can be thermally excited. We write delta E approximately equals 4 kBT. This is the energy window where occupation probability changes significantly. Let's work through another practical example using gold metal at different temperatures. Gold has a Fermi energy of approximately 5.5 electron volts. At 1 Kelvin, kBT is about 0.0000086 electron volts. The distribution is extremely sharp. Almost no electrons are thermally excited. At 300 Kelvin, kBT is 0.026 electron volts. There's slight broadening, but still only a tiny fraction of electrons near EF are affected. At 10,000 Kelvin, kBt is about 0.86 electron volts. Now there's significant broadening, and the electronic heat capacity becomes more substantial. The chemical potential mu in the Fermi-Dirac distribution is closely related to the Fermi energy. At zero temperature, the chemical potential equals exactly the Fermi energy. At finite temperature, mu of T approximately equals EF times 1 minus pi squared over 12 times kBt over EF squared. Notice the small correction that depends on temperature squared. For typical metals at room temperature, this correction is less than 0.01%, so mu remains very close to EF. Fermi-Dirac statistics continues to be crucial in modern physics and technology. In quantum computing, especially solid-state qubits, understanding electron distributions and energy levels is essential for designing and controlling quantum bits. Spintronics exploits both the charge and spin of electrons. The Fermi surface and spin-dependent density of states determine device properties. Topological materials exhibit exotic properties related to the structure of their Fermi surface. These materials may revolutionize electronics and quantum computing. In neutron stars, which are even denser than white dwarfs, both electrons and neutrons are degenerate. The Fermi energies are so high that neutrons become relativistic. Let's summarize the key concepts we've covered in this lesson. Classical physics predicted that electron heat capacity should be constant, equal to 3/2 nkb at all temperatures. But experiments showed systematically lower values, especially at low temperatures, revealing a major failure of classical theory. The solution came from the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state. Fermi and Dirac independently derived a new statistical distribution that incorporates the exclusion principle. The key insight is that only electrons within about kBt of the Fermi energy can participate in thermal processes. This leads to the prediction that electronic heat capacity should be linear in temperature, which matches experimental data perfectly. The dimensionless ratio, kBt over EF, determines what fraction of electrons can be thermally excited. For metals at room temperature, this is typically less than 1%. Fermi-Dirac statistics unified quantum mechanics with statistical mechanics, creating the field of quantum statistical mechanics that describes systems of many identical quantum particles.